Okay, I want to teach you another method of doing integration by parts, and I call it the tabular method. And what it does is it gives you a better way to control and keep track of everything if you're doing a long integration by parts. So if you can think back to the ones that we've done in the past, we had some where we were repeating the u du part to try and get it to cancel out. So the example I'm going to do here is the integral of x cubed times sine x. So those two things are unrelated, so it's a good choice. But before we had to do x cubed, or we would have to do x cubed maybe like 3 times to get rid of the cube. It'd go down to x squared, then x, then eventually it'd go away, and we'd have some trig function by itself that we could actually integrate. But that was a lot of work. So to kind of remind you what that looked like, in the integration by parts formula, the integral of u dv turned into u times v minus the integral of v du. So we had to take the derivative of u and the integral of v, and if the integral of the end was not integratable by a regular integral formula, then we had to repeat the process again. And then after that, we'd have another uv minus integral of v du, and we may have to repeat that process again until we got something that we could handle. So the diagram I got here just kind of shows you that that process gets longer and longer. And remember that there's steps in between here that you are integrating, taking a derivative of, and putting it all back together. And if you got chain rules and u substitutions, that takes even longer. Okay, so the method, the tabular method that we're going to do does just that. It takes a u, and in our case, our u is going to be the x cubed, and it takes a v, and our v will be sine x in this example I was talking about. And because we were trying to get that u to go away by taking derivatives, I've made a table. And at the top of that table, I've made one column that starts with x cubed, and I've made another column that starts with sine of x. So in the u column, we're going to take derivatives. Okay? Let me do that a little bit differently. Let's put it like this. Derivatives. So I'm going to make a new row for every derivative. Derivative of x cubed is 3x squared. Then I would repeat the process. The derivative of 3x squared is 6x. The derivative of 6x is 6. Derivative of 6 is 0. So that's an iteration each time that I have to do integration by parts. Now the other column, where I have the sine x, I'm taking integrals. So it looks simple when you just have a simple trig function like sine x. Sine x, if you integrate it, goes to negative cosine x. You integrate negative cosine x, it goes to negative sine x. You integrate negative sine x, it goes to cosine x. And you integrate that, you get sine. But remember, if you had like 2x in here, you would have some u substitutions, so it would get a little bit out of hand. So I'm taking one column and I'm integrating every time. I'm taking the first column I'm taking a derivative of, and the second column I'm integrating over and over. So what does that mean? Well, let's take this information off. And if we look at what we got here for a single integration by parts form, the top one is u, that's the x cubed, and the dv was the sine of x. Well, if u was x cubed, then the next row under it is the u prime, the 3x squared. And if the top one is dv, the next row under it is v, the integral of that. So what did our integration by parts formula tell us? It told us that if we integrate u dv, we get u times v minus the integral of v du. So we need u times v. Well, that's going to be a diagonal here. That is u times v. Okay? And across would be the v du. Okay, so if you go straight across, you get a VDU, which is the part that still needs to be integrated. If you take a diagonal, you get a UV. So if we keep repeating the integration by parts, we get new UV combinations all the way across. And that's what we want to do. So let's take this off again and see if we can do it this way. We will take this diagonal, and that is something we want. That's a UV. The next diagonal is another UV. We want that. It has been integrated. The next diagonal is another UV that has been integrated. The next diagonal is another UV that has been integrated. So this is working out very nicely, and the reason this lets us stop is because that U derivative eventually went to 0. So there could still be more stuff in the V column to integrate, but it would be times 0, so it would end. So we have all the UV combinations that we want, but there's one more thing we need to say about it. Okay, so if we come over here, and let me pick a color that I don't have on here. This purple's not here. So look, right here we did a negative sign. The next time we got integrated, excuse me, let me take that off. I put it in the wrong place, I'm sorry. So the first time the UV is positive. Okay. The second time the UV is negative. The next time the UV will be negative, negative. The next time it will be negative, negative, negative. So positive, negative, positive, negative. So if we go back to our UV combinations, we're going to attach a sign to each one of them. The first one will be attach a positive. Now it could still turn out to be negative if there's a negative in the UV combination. The next one will be negative, the next one positive, and the next one negative. And that would just repeat that pattern as you go down. So the integral of this thing we have up here will be x cubed times negative cosine. So that will be negative x cubed cosine of x. The next one will be negative from outside, 3x squared times negative sine x inside. So that would be a positive 3x squared sine of x. The next one will be a positive 6x cosine of x. So that would be positive 6x cosine of x. And the next one will be negative 6 sine. So minus 6 sine of x. We got messy again. And this thing should pick up a plus c at the end. Okay, so this is the integral of x cubed sine x dx by using this table. So we didn't have to go through and list a UV every single time and a V du and integrate over and over. We're able to do that systematically through the table. And this is very helpful if you have a large power here that you're trying to get rid of. Okay, we'll stop there for this one, and then we'll do some examples and see some exceptions.